transition culminates at an isolated point indicated by red here, or the critical point. And the critical point is such that you can go from the gas phase to the liquid phase and vice versa continuously. So this is water. If you now focus on the phase diagram near the critical point in the PT plane, you will get this phase diagram. Again, first order phase transition is shown, and here is the critical point. Now, many of you would know already in colleges that if, however, you cool the, or you heat or you cool the gas very rapidly without allowing the system to equilibrate, then you get a supercooled phase. Supercooling has an implication in the quark-gluon plasma QCD phase diagram that I will discuss. So there is a possibility of supercooling. So in fact, from liquid to solid, if you don't cool very slowly, allowing the system to be in thermal equilibrium at every stage of the cooling process, then you would get a glass. So we are all familiar with glass. Glass is metastable and can live forever almost. So let me get back to the phase diagram again. So you see, this is for a single component system like water. Now if you add one more component, you get another degree of freedom. This is what you learn in thermodynamics for the Gibbs phase rule. So now you have another degree of freedom, which is the chemical potential mu2 associated with the second component. And what was a line of phase transition, first order phase transition, has now become a surface from geometry. Okay, and then you have the possibility of a very fascinating thing, which again I'll show you in Vikasana's work, that you see, you remember you had a single point was a triple point, but now you have a line of triple points, and you have a liquid-liquid line, which is separation line, and that ends into what is called a critical end point. You can never actually make the critical point end point go all the way up to the liquid vapor critical point, critical line, because Gibbs phase rule will not allow it. So you have to have another element, a ternary mixture, to make this happen, but that can also be obviated if you have a symmetry breaking. So if you have a helium-3, helium-4 mixture, where helium-4 can exist in two phases, the normal and superfluid phase, then you have the possibility of given a multi-critical phenomenon called a tricritical point here. And so here is the line of second order phase transition, superfluid phase transition from the high temperature phase to the low temperature phase, and you have this two-phase separation of the helium-3. What is plotted is the temperature versus the concentration of this helium-3, helium-4 mixture. All these phenomena have relevance in Sinha's recent work on QCD phase transition, the 2020 paper that I mentioned, and its conjectured relation to the early universe as indicated. Next. So now I show a standard phase diagram which is known to the experts here in the audience for a transition from a chiral symmetric, again I'm using the word symmetric, chiral symmetric QGP phase, the quark-gluon plasma phase, which is chirally symmetric, to a broken chiral hadronic phase, which is here, across this first order phase transition. But you can also have the possibility of supercooling, as we discussed. You can supercool, and then the system is not in equilibrium. And then, of course, you have this very interesting phase diagram. And so here, Sinha has taken this picture to the arena of black hole thermodynamics. We've heard about a little bit of that from Roger Penrose, by making an analogy between gravitational confinement due to black holes and quark confinement of strong interaction. Supercooling is suggested to yield metastable quark nuggets, and an interesting simile is predicted between the Hawking radiation from the gravitational fields of the black holes and quantum tunneling of neutrons from the quark nuggets. Well, in the realm of speculation, let me add my bit, which, like the earlier one above, can be actively debated by this learned audience. I'm sure Sunil Mukhi is going to jump on me later on. Anyway, there is this curious ADS-CFT conjecture on a new uncertainty relation for the ratio of the viscosity eta to the entropy density through this lower bound. Now I have written the lower bound in terms of the Boltzmann formula that was also used in the Stephen Hawking Penrose radiation. It is the log of the number of microstates and the kV, but the entropy density is kV times log omega, so you eliminate kV, and here is a new kind of uncertainty relationship. So you see, the reason I dubbed this relation curious is because, as you all know, entropy connotes to a thermal equilibrium property, while the viscosity characterizes a transport property, not covered under equilibrium statistical mechanics and thermodynamics. However, the quantum Langevin equation approach, as we indicated earlier, is ideally suited to calculate both the viscosity given by the Coué formula in terms of stress-stress correlation functions and the entropy density within the same formalism. So, this connects to this enigmatic issue in condensed matter, which is called the glass transition, where if you supercool a liquid very rapidly, you get into a glassy phase where the heat capacity shows an anomaly, and so does the viscosity. So here is another phase diagram of where volume, enthalpy, or entropy is plotted against the temperature, and here is the viscosity, which rises very rapidly as you supercool. So there is the relationship between the viscosity and thermodynamic quantities. So this is where Vikas and I plan to do work at this old age on this ambitious approach in the context of quantum Langevin equation to apply to QCD phase transitions. Now, Mr. Chairman, I think you ordered me to stop at 1:30, so I have 3.5 minutes. Now, on institution building, Dr. Shom, the ECC director, and the present director of Saha Institute, Gautam, had already mentioned quite a bit. So let me very quickly show you the pictures. So let me, before that, just to say how well I know Bikash. Between 1976, the year that both of us came back to India, and 1999, I was away from Calcutta, he's back. He has always been a loyal soldier of the atomic energy. While I, the maverick, left atomic energy, went to universities and did some crazy things, as Sri Narayanan knows very well. And I made a re-entry to this city after a gap of 30 years to the SN Bose Center. In between, our professional trajectories had diverged, as I said. At this point, I digress a little and amplify my earlier point on why I feel Sinha epitomizes the confluence of the East and the West. And I hope I shan't offend my Indian physicist friends here. You see, institution building is not our forte, or trade, especially the Bengalis. I have no qualms in admitting that we learned it from our colonial rulers. More often than not, in our way of life, persona become more important and prominent than institutions, not in the eyes of the builder himself, but the minions who follow him. A notable exception of a great institution builder in Indian physics scene is Homi Jahangir Bhabha, who, like Bikash, was also trained in Cambridge. And a noteworthy indigenous local example is the nuclear physicist and pioneer astrophysicist Meghnad Saha, the institute named after whom we are being hosted at. By 1984, Vikas Sinha had moved from Trombay to Calcutta, first as the head of the computer and research facilities and later as the head of theory division before taking over as the director of the VECC in photos shown here. Subsequently, from 1992, he held the dual position of the director of the Saha Institute of Nuclear Physics. He retired from these two positions in June 2009. VECC, as Dr. Shom very correctly said, and very eloquently, he was already in possession of a room temperature cyclotron of a Berkeley design, K equal to 130. Slide here. Because Sinha's early challenge in WEC was to develop a superconducting cyclotron, this was a formidable task indeed because of the scarce know-how in the country for the requisite cryogenic technology for making superconducting wires. An accompanying task of winding nearly 42 kilometers of wire in the alpha and beta bobbins of the magnet proved to be yet another hurdle. Eventually, following truly arduous effort over a period of 12 years, after the foundation laid in 1997, the internal beam was sighted in August of 2009. However, the extraction of the external beam had proven to be extremely daunting. So here's a picture of the, this is now the medical cyclotron. So Dr. Shaw mentioned that a parallel push was given for the production of radioisotopes for the treatment of cancer tumors, for which it was necessary to purchase a medical cyclotron from Belgium. This was satisfying indeed. The journey that Sinha and his colleagues had embarked upon finally culminated in the city of joy, turning into a city of cyclotrons, being endowed with 3 of them, plus of course the radioactive ion beam facility, a project that is ongoing now. This is RIB slide. In addition, a photon multiplicity detector has been developed, which proved to be extremely useful in detecting the so-called azimuthal flow in the sulfur run at CERN. So, sort of fast forwarding again, as I mentioned, Sinha was also at the helms of affairs of this institute. Many of us would know that SINP plays a dual role vis-a-vis VCC, just as TIFR does to DRC in Bombay. But with all the security arrangements now, I feel that even SINP is becoming like VCC. But it's fair to say that it is because Sinha who took SINP to a higher platform, the international arena, by initiating lots of collaborative activities such as the FRENA project that Gautam mentioned, and I was very happy to learn from Tilak that they got the first FRENA beam just about a week ago. So as the director of VCC and SINP, Sinha had led the Indian team for participation in ion and antiproton facility with the acronym FAIR, another landmark international collaborative project other than CERN. I don't mention ALICE detector, etc., etc. Now the societal, so here is the picture of CERN, ALICE, CMS, Atlas, all these things are mentioned. It is amply clear, ladies and gentlemen, that the man Vikas Sinha is very much a synthesis of science and society. His heart is in search for societal benefit of fundamental science. Mentioned the medical cyclotron already. On Sinha's deep concern for the society, it is worth mentioning the project on extraction of natural helium from thermal springs at Bokreshwar and Tantulai, about 200 kilometers northwest of Calcutta. I show a picture here where Devashish Ghosh is there. You see, there are many people who work in the background for the conference to be successful, and Devashish's contribution is enormous. One research follow-up of that project is the intriguing correlation between the enhancement of helium content and earthquake and volcanic activities. Finally, interface of science and philosophy. Since a full day is devoted to day after tomorrow on the Tagore Center, I shall be very, very brief here. True to his cultural upbringing, Sinha is very much a holistic personality who views science and philosophy as the two sides of the same coin. Here he is in sync with Rabindranath Tagore, who in his astounding repertoire on literature saw nature as a living laboratory of science. TCN NSP is an attempt to carry forward the legacy of Tagore, the great visionary. Here is a photo of the poet visiting the Sinha family in Calcutta. Mr. Chairman, I come.
Thank you very much, Dr. Dattagupta. While perhaps Dr. Antinori makes his preparations, perhaps you'd be willing to answer a question or two.